definite integral one and see what we get. Alright, so we're going from 0 to 1. Now, if you want to use this to get change in x, by all means do it. But if I'm using what? 4 subdivisions. Draw this again so one can see this. 1, 2, 3, 4. And if you're using 4 subdivisions, what's that width right there? That's your change in x. I like when you can visualize change in x rather than thinking it's somewhat abstract math formula. Oh, what was change in x again? B minus a over n. Can you see it?
It's 1/4.
It's 1/4. And that's what I mean. Don't ever let this, because my worry is you do this formula and you accidentally put a big 1 here, or put a big 1 there, or put a big 1 there. It's like, no, in this problem, because they said n equals 4, change in x is that width of each subdivision. In terms of trapezoid, that's that height. So there's your change in x. But obviously, we could have got it anyway. What's 1 minus 0 over 4? That's 0.25. So I'm getting 0.25 or 1/4 divided by, all right, it's trapezoid, divided 2 or is it 3?
2.
So we divided 2 with trapezoidal rule. We divided 3 with Simpson's rule. All right. Now I'm going to do f of 0. So it would be sine of 0 plus.
2 sine of 0.2.
Good. Put the 2 down. 2 sine of, what's this next number here? That was 0. 0.25? I'll put that in.
Squared.
Notice I'm putting it into the, yeah, I should write sine of 0 squared. Every time I'm taking the x value, 0, 0.25, that's a 0.5, that's a 0.75. I'm taking each x value and I'm substituting it into the function. 2 times sine of 0.25 squared plus 2 times sine of 0.5 squared plus 2 times sine of 0.75 squared, and the lonely, lonely n doesn't get the 2, it's just the sine of what squared?
1.
Now this can throw students off. What was n equal to in a problem? When somebody hitting it on your calculators, that's wonderful, because you're going to help us get this answer. Don't let this bug you. N equaled what? 4. 4 trapezoids, right? Look carefully at my math. How many numbers do you see between the brackets? This will happen. So I didn't want that to bug you. That's exactly what will happen. You go, see, I don't want you to start being on a test and going, why am I at 5 and I'm doing something wrong? This is exactly correct. But with n equals 4, you still have your 4 subdivisions. It's just what came out of it when we did that math. So if n equaled what? 12? You'd have 13 values in there, wouldn't you? That's what would happen. Hey, what is 1/4 divided 2?
1/8.
So some of you might type 1/8 and then type all this into your calculator. Be careful because of all the parentheses, sure. Just be very, that's all we say. What mode? Because it's a trig function. Will you check your mode, make sure it's in radian mode? Another reason I want to do this problem with you, I didn't want you to go home tonight and go, why am I not getting the answers in the bag? It might be the mode, you might be in degree mode. These are radian values. 0.25 radians. 1 radian. I did it, so I'll see if you got what I got.
Hold up. 0.31597.
That's what I got. Who got that? Thank you very much. I get the same. And when you get 0.3159, what was after the 9?
7.
0.31597. What was after the 7? Go ahead, Armando.
2 sine. Are you squaring sine or are you squaring 0.5?
Great question. That's a really good question. I am squaring the 0.75 because of the way it's written. It's not like there's a square here. So in this case, it's like I'm only doing sine. The calculator automatically puts a parentheses, and I'm typing 0.75 raised to the second, then closing out the
I'm talking
parentheses.
about the 0.5. It looks like you're squaring sine. See the 2 plus 2 times sine
7.5 is squared.
up to the right.
Right there?
Yeah.
Oh, I got you. Armando, thank you. I'm going to put this. He's saying you got a typo in that writing, and I appreciate that. This should be 0.5 raise to the second and then close the parentheses.
Oh, oh.
No, that's exactly right, and thanks for catching that. Each one of these becomes a sine of x squared, different from what? Different from stuff we've seen before where they write this, right? Which means all of sine of x squared, so you're right. So Armando, thank you again, right there, that 0.5 squared is the angle, the radian angle. And we get 0.31597. Is everyone getting there? Now, is someone who use Math 9 to see the exact? It's about
3.10.
same amount of decimal places.
Sure, 0.310268.
So when we're using Math 9 on our calculators, CID 384, let's run a definite integral and say, hey, and just make sure in radian mode. Let's see, man, how close was this? What was it again?
0.310268.
And we won't do it now, Kate. I know if you go, if you wanted to, you go, what's my error? You can see how close it is. Just when n equal to 4 trapezoids. Hey, we don't have to do it right now. But I do want to point out, this was concave up, right? All right, cup was concave up. And what happens when it's concaved up? Well, let's let I equal the exact integral. The trapezoidal rule will always be this overestimate, which it is in this case, do you all agree? And you know who would be a slight underestimate? The midpoint rule. If you're curious. The midpoint rule would have been a slight underestimate. Trapezoid slight overestimate. Hey, we will not compute it now. Well, once everyone has this copied down, can we just talk about, you have to compute it. What would you do? What would be different about Simpson's rule? Because there's not much changes in these numbers up here. It's not much that we have to change. You might put it in your notes. You don't have to compute it. It's just what would you do? It's not much.
It would be 112.
I'm okay if I write over this thing? Good, so I'm just going to go. If we use Simpson's rule, this changes to a what? All right, so I'll go. That becomes a third. But this stays the same. That number there turns into 4. Then it alternates. 4, then 2, then 4. And you would keep alternating this. Mark that we knocked out the 2. And then you add the lonely thing. So even if n equals 20, if you had 20 of these, you'd go initial number, and you have 4, then a 2, then a 4, then a 2, then a 4, then a 2, then a 4, then a 2. Then you'd have the second to last coefficient would be a 4, because n equals is even, and then the last number would be lonely. So you will never, ever, ever encounter, in Simpson's rule, you'll never, ever encounter that the second to last number here, this, is a 2. It always go 4, 2, 4, 2, 4, 2, 4, 2, 4, then that last number. Or, in this case, what? 4, 2, 4. Then this. Maybe 4, 2, 4, 2, 4. Then this. Because we're always going to have n even. I don't want you to think, like, if you ever found yourself going 4, 2, 4, 2, and then this, just go back and go, wait, I made an error somewhere. Well, everything else is the same, right? Cool. Simpsons use parabolas. Hey, now we're going to do this from a table. Let's do this from a table. Practice problems that I gave to you, I gave you at least a couple tables. Not bad, because on this time we don't have to plug the number into some equation like sine of x squared, right? I like that. It's just going to be the y values, if you want to call them the f of x values, the y values will be right there in the table. So the problem we'll do together, this is number 40. And it's in section 7.7. So I'm going to put this table on the board here. All right, they got x, and I got f of x. 0, 3, 6, 9, 12, 15, 18. And I'll tell you what all these function values are in a second. not sure why. Alright. 0, 3, 6, 9, 12, 15, 18. And here comes f of x. 9.8. 9.1. 8.5. 8.0. 7.7. 7.5 and 7.4. And the table shows a force function. F of x, where x is measured in meters, and f of x is in newtons. Here's the question. Use Simpson's rule. To estimate the work done. And moving an object. A distance of 18 meters. We'll copy this. Hey, as you're copying, if you recall Connor's question, about 20 minutes ago, they will always give you the end value, like use n equals 8, or use n equals 10, or use n equals 6, except for these tables. They don't tell us, I would have written it down for you, use Simpson's rule. And so we're going to use as many as we can in terms of subdivisions. So what we're saying is, yeah, we're going to make each time this change in x, what's the distance from here to here? 3. That's your change in x. That's the change in x we're making. If you want to make a picture of it, you do 0 to 18, and you're like, I'm going to use as many as I can. So 0 to 3. That's your change in x. Cool. Does that make sense? It's a really important question. When I give you these tables, I want you to use as many subdivisions as we can from the presented data. These are real data values given. We want to somehow, use Central to estimate the work done. We know that work equals, well, force is constant, force times distance, but it's not constant, so we're do the integral from a to b of f of x dx. But we're just going to estimate this with right? Work equals the integral from a to b of f of x. Hey, what are some other examples you see from the book before we work out this problem? They may give you velocities, and they'll ask you to estimate the, what do you think? What would be the integral of that antiderivative? It'd be, well, that'd be derivative. So we go the other way. Distance, right? So if they'll give you velocities of, say, a vehicle, a motorcycle, a car, at different points, and okay, can you estimate the total distance? Just to give you an example, if you're driving home tonight with your friend, you could sit there, don't crash or anything, but listen, every 30 seconds, look at the speedometer. I'm serious, like if you're driving, like say it's for 10 miles, but just every 10, just look and write it down, every 30 seconds, write down the speed. And so you'd have a table of a bunch of what? A bunch of velocities, right? Now sometimes the velocity may be 0 because you might be at a stoplight, do you agree? But anyways, you'd have all these velocities, or this is the time period, And then if you use one of these methods, you could, Simpson's rule or what? Trapezoidal rule, you could estimate the total what? Distance that you're traveling. Where I know you're sitting there going, dog, look at my speedometer. Right? It's right there. I'm like, look how many miles I went. But that's a way you can estimate how far you went, if you like doing it. So, and I won't joke about doing that for bonus, because I once did that. And the next day, a student came in with this gigantic poster on a line, took up like this entire board. Where she really did that with her friend. They drove down to like Annapolis. It's like all broken up. So the thing was like this. Yeah, but every time they hit a stoplight, it was what? And the values were 0. But that's what's going on here. Bunch of velocities, estimate the distance. Right? Rate of change of water flowing out of some tank, you can estimate the total volume of water that leaked out of the tank. Right? But in this case, we have all the forces, we're going to estimate the work. All right. So does everyone agree that change in x is going to be 3? Cool. Armando.
Is that kind of like how they calculate the oil spill on the Gulf Coast?
They definitely can use some calculus in there because, I mean, when you talk about, especially when you think like even off like, you remember the one off Louisiana? When all you see a videotape and all you see is a hole and you see in the water and all you see is what? Oil just what? Going like this. Sometimes you can be going, how much is coming out? How fast is what? And so you get an estimate of what's the total amount of, you know, it's good estimate technique. Estimate the total volume that came out of there. Leaked over like an hour, 2 hours, 24 hours. Okay. Now when I'm going to work this problem, hey, one more thing again. I just want to, you hear me saying this over and over again. This change in x. So you crush this during a test. That change in x there is not 18, is it? What's the change in x we'll use? 3. That's exactly, I'm going to use change in x equal to 3. And so what you have, you can look at that image. 0 to 18. You're like 3, 6, 9, 12, 15, 18, but there's your change in x. That little subdivision. It's the width of each subdivision. That's what that change in x is. I didn't want you to think change in x was, oh, from A to B. So I'm going to start it out. Change in x over 3, right? Simpson's rule? Change in x is a 3. And then I divide by a 3. I think I have enough room right here. This will be better than the one with the sine of x squared because I won't be so worried about the parentheses. What's the first number here? Oh, here's a common error in test. So I'm going to start out with this. So the student knows about the 4s and the 2s and the 4s and the 2s, right? They look at the table and they go like this. And this is wrong. Anybody know what I'm doing wrong?
You're reading x value out of f of x.
No, I've seen this before. They're like, oh gosh, they were just reading the table incorrectly. I need to use what here? The f of x. So this right, these are f of x values. These are the y values. And I'm accidentally doing 4 times x values. 4 times. These are the numbers right here, the y values. So let me fix it. Because I know it's a table. You're like, this is going to be simple. You get the change in x down 3. So the first number is a what? 9.8 plus, start with a 4, right? 4 times. And now it just flows. 2 times. Okay, run out of room. I'll just go down here. Plus 4 times. 8. What's next? 2 times. 7.7. Plus 4 times. And lastly, only 7.4. See how this penultimate term had a 4 as a coefficient? Now this is bizarre one. I actually did look. 1, 2, 3, right? In terms of this. 1, 2, 3, 4, 5, 6. If you're curious, n equals 6. Don't let this bug you that I really have some of the numbers in here. 1, 2, 3, 4, 5, 6, 7. I thought I would look at that at the end. Y'all notice n equals 6? Yeah. How many? 1, 2, 3, 4, 5, 6. Trapezoidal rule would also have 6. That's the most we can use with trapezoidal, and that's the most we can use with Simpsons. All right, what are y'all getting?
148.
Someone else get 1.8? What's the units? Starts with letter J. Joules, yeah. Because then when they had X was measured in meters, the force was measured in newtons, my work will be 148 joules. Cool.
You have to put a estimation symbol, like a round across.
I love that. If you didn't, I wouldn't mark off, but I love it. You're like, hey, we're just estimating this, right? We're using an estimation technique. What's so neat about this, though, goes back to Armando's problem. I mean, this can happen in real life, right? People don't have a function to model this, but we can just get an estimated. Another technique is you can use regression. Anybody ever done regression? You can get like a regression curve to go through these points. Maybe some kind of, not to be a straight line, and then you use that, and you can do a definite interval of that. Any questions on that? And again, we don't have to write it out, but we don't even have to solve it. What would trapezoidal rule do here?
I just had a
Oh, go ahead, question.
Could you go over the delta x over 3 one more time? So the delta x over 3 is part of the formula, but where did you get the 3 on top of the delta x?
So this is called the delta x.
The difference in x.
Yeah, but what it is, it's not the entire like region. It's probably one of the major errors made on tests. Come on, and people think change in x, I see it went from 0 to 18. I'm thinking change in x is this. No, it's only the width of one subdivision. And in this case, they didn't tell us what n is equal to, which throws us off. So we're going to use as many as we can.
So if you would have used, say, 6 to 9.
Oh yeah, 9 minus 6 is what? 3. You could have done 18 minus 15. That's what you'll do with Simpson's rule. And same thing with trapezoidal rule. I mean, it's a really good question. You go, what am I going to use? And the big, I don't want you to think accidentally that I put a big 18 here. I mean, there's a math element to it, but they didn't tell you n. Now, do you notice n equals 6? We're going to do 6 subdivisions. You could have done that and said, all right, I'm going to make 1, 2, 3, 4, 5, 6 subdivisions. Then you could have done this math, 18 minus 0 over that 6, giving you the what? The 3. I prefer, it's up to you, but I prefer that you look and visualize, go, that's my change in x. I can see it. It's just going to be the width of each subdivision. Now I do have to point something out, I don't want to confuse anybody. If you did use midpoint rule, then we need midpoints, don't we? So if you want to think about it carefully, midpoint rule, I don't think we use change in x of 3. Because look, there I midpoint, no, they didn't, I don't know what's going on at 1.5, you agree? So by midpoint rule, I think the most we can use is what? We do one rectangle from there to there, right? 0 to 6, then we can do the what? 6 to 12, and then the 12 to 18, do you agree? So how many rectangles would that be?
3.
1, 2, 3. Anyone see that? If you did it with this, it would be easier to see it here. If we had to do rectangles and do midpoint rule, we need midpoints. There's 0, 3, 6, 12, 15, 18. We'd say, okay, we got that number. We get in the midpoint, there'd be one rectangle right there. Then we can do another rectangle here using the midpoint 9, and but drawing a picture always helps. Always helps. Hey, we're going to do the air bounds in a second, but just real quick, what would you do if it was trapezoidal rule? This becomes a what?
2.
2. And all these become what?
2.
2. Slight difference. Got it. All right, let's talk about air bounds. So for this problem, this is neat. This is how we end section 7.7, everyone, is how accurate are we? Especially with these intervals like sine of x squared. We run this through a program. We store this into a computer. We don't want to say, hey, use 1,000 every time. Let n equal to 1,000. That can take up a lot of time, true? So we're trying to use the fewest amount that you need for the desired accuracy. It saves a lot of time. Has anybody ever seen these old scientific calculators? I mean, it's just neat. We used to race them on the factorial button. So I'm talking about like a scientific calculator from the 1980s, and I'd race my calculator versus my friends. We both bought them at Radio Shack. I'd say, all right, let's do it. We type in like 65 factorial into calculator and hit enter. But what's the calculator doing? 65 factorial means 65 times 64 times 63 times 62. they both had to what? Race through that. But it was running through a program, you follow me? And so there'd be a slight delay. We'd hit enter and be like, and then my screen would pop up with the answer. Or maybe his would beat mine. Now with these, it's just what? It's instant. It's like, boom.
Oh, that's
With upgrade
Casio.
technology, right. But yeah, it'd be like a Casio EP500 versus the Radio Shack version, etc. But it's kind of neat, but that's what we're talking about now. We get these error bounds to limit the amount of times or the number of iterations. So let's do one with trapezoidal rule. This T stands for trapezoidal, that M stands for midpoint rule. This N stands for Simpson's rule. Do you notice we have to do second derivatives in something like this? May look weird there, don't let this be intimidated whatsoever. I thought we'd start with the integral from 1 to 2 of natural log of x. Now we know how to get that exactly, don't we? Anyone know how to get that?
1 over x?
Or does anyone know how to evaluate that definite integral exactly? Well, wait. I like yours better. Because that would require integration by parts, wouldn't it? I heard you say 1 over x. I prefer that integral. The last one would have needed the integration by parts. Do you agree? Natural log of x. Let's use 1 over x. All right. So we're going to do 1 over x dx. We're not going to get it exactly. What's the integral of 1 over x? Natural log of x. You plug in a 2 and a 1, you get natural log of 2 minus natural log of 1. What I want you to use, and how do they word this in the book? How large do we have to choose then? That's what they ask. How large do we have to choose n? We're going to estimate this with a trapezoidal rule. Well, how large do we have to choose n so that trapezoidal rule approximation are accurate, in this case is, to within 0.001. Okay. How large do we have to choose n? And this number of subdivisions. So the trapezoidal rule approximation to that integral is accurate to within 0.001. Someone can meet 0.0001. .0001. That will give it a few more subdivisions. Okay, so a question like this, and I hope this gets your curiosity going, because now we're saying, boy, we can figure out using the trapezoidal rule how many of these subdivisions, n, the n value, we need so we can be that accurate so we can actually store this into a computer. Tell when it's, use this amount of subdivisions rather than just using n equal to 1,000 every time, which would be time consuming, true? On a computer. So if we're using trapezoidal rule, everyone, here's the error bounds formula. It's k times b minus a cubed over 12n squared. Alright? Now, this k value is some constant such that the second derivative and its absolute value of the second derivative, that function right there, is always less than or equal to k. So the first thing we have to do, here's the function, f of x equals 1 over x. We got to find the first derivative and then we got to find the second derivative, don't we? That's our first step. But we're going to use the error bounds formula to calculate this. But that k value comes from the absolute value of the second derivative of f of x. So we're going to start there. F of x equals 1 over x. which is x to the what? Negative 1? What's the derivative of x to a negative 1?
Negative 1 x to
Negative 1 x to negative 2? I like it. What's the second derivative? Two x to the negative 3. And what's another way to write that?
2 over x cubed.
2 over x cubed. Okay, we got it. Now we got to decide what to use for k. So when we got the second derivative, right? So don't let this intimidate you at all. This is kind of fun. Because we're just going to plug it into the formula. We're going to solve for this letter n. But we did have to start with getting this k value. Now we know what the second derivative is, right? So we're looking for this k value such that 2 over x cubed is always less than or equal to k. Always, no matter what, on the interval from 1 to 2. Now you might say, well, why don't you just use 1,000? And when the absolute value of this is always less than 1,000, remember what we're saying, we're like, get that number, the best number we can use. So what were the limits from a to b? Say go from the a value to the b value. So let's plug them in. And if you plug 1 in there, what do you get? What's 2 over 1 cubed? 2. I'm going to write that down. That's if I plug a 1 in there. Plug the other number in there. Oh, and what is the absolute value? In case it came out negative, you make it positive, right? Now when I got this by plugging in what? I plug in the endpoint a equals 1. Would you now plug the value b into that? What do you get? 2 over 2 cubed? What's the absolute value of 1? 2/8 or 1 what? 4? All right, which number is bigger? That's the number we got to use.
2.
We're going to use k equals 2. And I'll stop to make sure everyone knows why we're using k equals 2. Why am I not using a smaller number? I plugged in one endpoint, 1. Second derivative is 2. I plugged in the other endpoint, 2. And I got a what? 1/4? We've got to come up with a k value, so this is what? Here's the word. This is always, no matter what, over that interval, the second derivative is always going to be less than or equal to a what? 2. Does that make sense? I could have used 1,000, but we're like, my goodness. Use the smallest number you can that's possible, but I couldn't use the 1/4. Because do you agree, everyone, the second derivative over that interval is not always less than a 1/4? Cool. Does everyone know why reason 2?
Cool. Trying to maintain that condition to be true.
That's right. Make that condition to be true, it's always got to be true. That's why I put the word always. Because it always has to hold over the entire row. So I'm going to use k equals 2. And I know you're going, can't you use k equal to 10? Yeah. I mean, 10 holds true, but this is the best number, right? This is the best number in terms of we want the lowest that we can use. So it always holds true. All right, now, let's write this out. What do we have here? This error, which is what?